Your notes are already dead. The moment you write something down in Notion, Obsidian, or Rome, it's to decay. You stop revisiting it. You forget where it lives. And 6 months later, you rebuild the same mental model from scratch because your own knowledge base failed you. This is the PKM graveyard problem, and almost every developer I know has fallen into it. Then in early 2025, Andrej Karpathy, the man who built Tesla Autopilot's neural stack and co-founded OpenAI, dropped a GitHub gist. No press release. No product hunt launch. Just a raw text file describing something he called LLM-Wiki, a personal knowledge base where an LLM doesn't store your notes, it reasons over them. It becomes a queryable, living extension of your own memory. Within 48 hours, it hit the top of Geek News with 156 upvotes. Developers were not just impressed, they were unsettled. Because Karpathy had named a problem they all felt but couldn't articulate. By the end of this lecture, you will know exactly whether this system should replace your current workflow and what it will actually cost you to build it. Here is what made this moment different from every other AI productivity hype cycle. It wasn't just one person's idea catching fire. Within the same week that Karpathy's gist went viral, Garry Tan, CEO of Y Combinator, independently released GBrain, his own open-source personal knowledge system built on top of LLMs. Two of the most technically credible figures in Silicon Valley, working in parallel, arriving at the same architecture. That is not a coincidence. That is a convergence signal. In the history of tech trends, when independent high-signal actors converge on the same solution simultaneously, it almost always means the underlying infrastructure has quietly crossed a threshold. In this case, LLM inference costs had dropped to the point where running a reasoning layer over your personal notes was no longer a research project. It was a weekend build. The AI PKM space had been gestating for years inside tools like MemAI and Notion AI. This moment was different. This was practitioners, not product managers, deciding to build for themselves. And when builders build, the real architecture emerges. But here is the uncomfortable question. If the idea is this obvious, why aren't you already running it? Let me be precise about what this lecture will and will not give you, because I have watched too many developers waste a weekend building a system they have been in 2 weeks. By the end of this 6-chapter series, you will be equipped to make 3 specific, consequential decisions. First, does LLM-Wiki actually fit your workflow? Or is it architectural overkill for how you actually use notes? Not everyone should build this. Second, if you do build it, which stack, the Obsidian plus RAG plus MCP that practitioners are currently converging on, or a simpler document text approach, matches your real retrieval patterns? Third, what is the true implementation cost, not the optimistic weekend estimate, but the actual maintenance burden 6 months in? These are not theoretical questions. I will give you a judgment framework with hard criteria for each. And here is a micro benchmark to calibrate your expectations right now. Developers who successfully run LLM-Wiki systems report spending between 2 and 4 hours per month on maintenance. But the ones who abandon it report spending that same time in the first week alone on setup that never stabilizes. The difference is architectural decisions made in the first hour. That is exactly what we are going to front load. Now let me show you the failure mode that kills most PKM systems before they ever become useful. And while LLM-Wiki, if built incorrectly, falls into the exact same trap. Every knowledge management tool ever built makes an implicit promise. Capture everything, and you will be able to find it when you need it. Notion, Evernote, Rome, Obsidian, they all optimized for retrieval. Better search, better links, better tags. But here is the brutal truth. Retrieval is not the bottleneck. You do not fail to remember things because your search is bad. You fail because your notes are fragments, half-formed thoughts that made sense in context, but are meaningless 6 months later without that context. An LLM-Wiki is not a better search engine. That framing will kill your implementation. The real promise, and the real difficulty, is building a system that reasons over your fragments and reconstructs context on demand. The distinction sounds subtle. The implementation gap is enormous. Most developers who try to build this end up with an expensive, slower version of semantic search. A PKM graveyard with a vector database attached. In the next chapter, we are going to dissect exactly why every PKM tool before this moment was architecturally incapable of solving this, and what structural change makes LLM-Wiki categorically different. Let's be honest, we've all been here before. A shiny new PKM tool promises to fix how you think, and 6 months later your notes are a graveyard of half-formed ideas nobody can find. This isn't a personal failure. It's a design failure into every tool we've used for the past 15 years. The Evernote era gave us folders, digital filing cabinets that worked great until you had more than 200 notes, and suddenly couldn't remember which folder held what. Then Notion arrived and said what if folders had databases? A genuine leap, but it introduced relational complexity that most users simply never mastered. Rome research flipped the model entirely with bidirectional links. Your notes could reference each other like a web, not a tree. Obsidian refined that, with local-first storage and a plugin ecosystem. Each generation solved the previous tool's worst problem. But here's what none of them ever solved. And this is the single insight that makes everything Karpathy built different. Teaser: the flaw I'm about to show you is so fundamental that it didn't matter how beautiful your graph view was. Your knowledge was still effectively dead on arrival. Here is the core pathology that every single one of those tools shared, and why it matters to you as a developer. All of them treated knowledge as a storage problem. They competed on how well they could help you put information in. None of them seriously addressed how you get meaning back out. Think about what happens when you search your Obsidian vault for authentication. You get every note that contains that exact string. But what about the note where you wrote JWT felt wrong for this use case and never used the word authentication once? That note is invisible to you. This is the semantic gap. Your knowledge system speaks in keywords, but your actual thinking happens in context and relationships. The manual link burden compounds this. Every connection between ideas requires a human decision. Do I link these two notes? Most of the time, you don't, because you're in flow. Your writing and stopping to curate links breaks the creative moment. So the graph stays sparse. The connections that matter most, the ones you'd only realize exist weeks later, never get made. Question: so what would a system look like that closes this gap automatically? That's not a rhetorical question. We're going to build exactly that. But first, let's confront the number that kills most PKM ambitions before they start. Now, here's the uncomfortable data point that the PKM community doesn't like to talk about. Studies and community surveys consistently show that the majority of developers who adopt complex PKM setups, the full Zettelkasten, the linked Obsidian Vault, the color-coded Notion workspace, abandon them within 3 months. Not because the tools are bad, because the maintenance overhead exceeds the retrieval value. You spend more time organizing your notes about a topic than the notes ever save you when you need them. Tiago Forte called it building a second brain, and the metaphor is seductive. But your actual brain doesn't require you to manually tag every memory before it stores it. It doesn't ask you to decide whether a thought belongs in projects or areas before you're allowed to think it. The second brain myth sold us a productivity fantasy with a hidden subscription cost: your daily attention forever. This is precisely the trap Karpathy identified. The solution isn't a better organizational system. The solution is eliminating the need for manual organization entirely. Payoff of that paradigm shift is exactly what we'll unpack in the next section. Because when an LLM becomes the interface to your knowledge, the entire maintenance equation inverts. Let me make this concrete with a side-by-side comparison, because the difference is not incremental, it's categorical. Imagine you're 6 months deep into a project and you need to remember why you rejected a particular API design. In a traditional Obsidian Vault, type API design decision into the search bar. You get back 3 notes that contain that phrase. You open each one. One is from a totally different project. One has the conclusion but not the reasoning. One has the reasoning but was never linked to the relevant project folder. You spend 12 minutes and leave less certain than when you started. Now, the same question to an LM-augmented vault. Why did we avoid REST for the notification service? The system doesn't search for keywords. It runs a semantic similarity search across your entire vault using vector embeddings, finding every note that's conceptually related, regardless of the exact words used. Synthesizes those fragments into a coherent answer grounded in your actual documented thoughts. The delta here is not a feature improvement. It's a fundamentally different relationship between you and your own knowledge. Question: but wait, doesn't this just mean you're querying ChatGPT over your notes? That's a common misconception, and it's exactly what RAG was designed to prevent. Let me show you why the distinction matters enormously. RAG, Retrieval Augmented Generation, is the architectural pattern that makes this possible, and it's worth understanding precisely what it does and doesn't do in the PKM context. RAG is not a chatbot bolted onto your notes. That framing leads to a critical mistake, treating the LLM as the knowledge source. In a pure chatbot, the model answers from its training data, which ends at a cutoff date, and knows nothing about your specific projects, your decisions, your context. RAG inverts this. When you ask a question, the system first retrieves the most semantically relevant chunks from your knowledge base using vector embeddings, mathematical representations of meaning, not words. Those retrieved chunks are then injected as context into the LLM's prompt. The model's job is not to know the answer. Its job is to reason over your documented knowledge and surface what's already there. This is knowledge grounding. The LLM becomes a reasoning engine over your personal corpus, not a replacement for it. The practical implication is enormous. Your knowledge base stays in markdown files you own. The LLM can be swapped out. The retrieval layer can be upgraded. Your data has no vendor lock-in. Teaser, this architecture has one more property that Karpathy pushes further than anyone else, and it's the reason his approach produces something that genuinely compounds in value over time, which is what we'll unpack right now. Now we arrive at the insight that separates what Karpathy built from everything that came before it, and it's deceptively simple when you hear it, but profound in its implications. Karpathy's framing is this: the LLM-Wiki is not a search tool. It is not a chatbot over your notes. It is a living model of your reasoning that becomes more accurate as it absorbs more of your thinking over time. The distinction is everything. A search tool is static. It retrieves what you put in. A living model is generative. It can surface connections, surface contradictions, and answer questions about how you think, not just what you wrote. Every time you add a note, you're not filing a document. You're training a more accurate representation of your own cognitive patterns. The wiki grows into a system that understands the gap between what you know and what you need to know in any given moment. This is the compounding effect that makes the approach categorically different from every previous PKM paradigm. Most PKM tools depreciate. The more notes you add without perfect curation, the worse retrieval gets. Karpathy's model appreciates. More inputs mean a richer, more precise model of your thinking. And here is why this matters immediately for you as a developer. The stack to build this, Obsidian, RAG pipelines, and MCP, is not theoretical. It is deployable today, with open source components, on your own machine. In the next chapter, we are going to break down exactly how that stack fits together, without the hype, with real architectural trade-offs you need to understand before you commit to building it. Let's cut through the tool wars immediately. Obsidian wins as the data layer for one reason that no competitor has matched: your notes are just files. Plain markdown files sitting in a folder on your disk. No proprietary database, no cloud lock-in, no API rate limit standing between you and your own knowledge. When Karpathy talks about building an LLM-Wiki, this is the non-negotiable start point. The LLM needs raw file access, and Obsidian's local-first architecture hands you exactly that. The plugin ecosystem adds powerful graph views and templating, but the real superpower is simpler. Any script, any model, any pipeline you write tomorrow can read these files without asking permission. But here's the thing most tutorials skip entirely. Obsidian's strengths are also a trap if you don't understand where they end. Now for the part nobody puts in their YouTube thumbnail. Obsidian, out of the box, is a sophisticated text editor with a graph view. That's it. There is no semantic search. The built-in search is keyword only, which means if you write a neural network in OneNote and search for deep learning architecture, you get nothing. There's no LLM reasoning layer, so the tool cannot synthesize across your notes or answer questions about your own knowledge. The plugin landscape is fragmented. The Smart Connections plugin, the Text Generator plugin, the Copilot plugin all do overlapping things with different quality levels, and none of them compose cleanly. And sync is a genuine engineering problem the moment you want your vault on multiple machines or shared across teams. These aren't complaints. They're the exact gaps that define what the rest of the stack needs to solve. Knowing the limits is how you avoid building a Rube Goldberg machine instead of a real system. Here's where most developers waste weeks. They set up Obsidian, dump all their notes in, then try to bolt Raggy on top, and get terrible retrieval quality. The reason is structural. Raggy doesn't retrieve notes, it retrieves chunks. And if your notes are 3,000-word stream of consciousness documents, your chunks will be incoherent fragments that confuse the LLM rather than ground it. The fix is to design your vault structure with chunking in mind from day one. Atomic notes, one concept, one note, become natural chunk boundaries. Front matter metadata like tags, date, source, and topic gives your vector store filterable fields for pre-retrieval narrowing. A consistent folder convention, such as separating fleeting notes from permanent notes from project notes, lets you scope retrieval to relevant knowledge domains. This is the unglamorous infrastructure work that determines whether your LLM-Wiki actually works in 3 months, and it's the part Karpathy's workflow implicitly depends on. The vector database setup we're about to cover will make or break depending on these decisions. The embedding model is the most consequential decision in your RAG stack, and almost everyone picks wrong because they benchmark on general datasets that have nothing to do with personal knowledge. Let's be precise. OpenAI's text embedding 3 small costs $0.0 per million tokens. For a typical 5,000 note vault at 300 tokens per note, your initial indexing cost is under $0.0. That's not the problem. The problem is latency and privacy. Every query hits an external API, your notes leave your machine, and if OpenAI changes pricing or deprecates the model, you re-embedded everything. The local alternative is Nomic Emb Text, an open source model that runs on CPU at roughly 150 milliseconds per query on a modern laptop, costs 0, and keeps your data local. Quality-wise, Nomic Emb Text scores within 3 to 5% of embedding 3 small on MTEB retrieval benchmarks, which for personal knowledge retrieval, where your notes are stylistically consistent, often means no perceptible difference. My recommendation, under 2,000 notes, use OpenAI for zero setup speed. Over 2,000 notes with any privacy concern, Nomic embed text via Ollama is the serious choice. The embedding model is only half the retrieval story, and the other half is where most setups fall apart. Now you have embeddings, where do you store them? This is where the industry defaults lead you toward over-engineering. Pinecone is overkill. Weaviate is overkill. For a personal knowledge base running on your laptop, you have three realistic options and the benchmarks are surprisingly clear. Chroma is the default recommendation in most tutorials because it's easy to set up with Python. 2 lines to create a collection done. But in practice, Chroma's persistence layer has had stability issues, and its memory footprint grows aggressively with large vaults. GBrain runs as a local Docker container, has significantly better query performance at scale, roughly 40 milliseconds versus Chroma's 220 milliseconds at 50,000 vectors, and its filtering API is genuinely powerful for metadata scoped queries. The dark horse is SQLite VSS SQLite extension that adds vector similarity search, 0 additional processes, your entire knowledge base in one DB file, and for vaults under 10,000 notes the query speed is competitive. The honest recommendation: start with SQLite VSS for simplicity, migrate to GBrain when you hit 1,000 notes or need advanced filtering. The retrieval pipeline sitting on top of these is where the real architectural decision lies. Here's the claim that will save you months of debugging: pure vector search on personal notes is a bad idea. I know that sounds counterintuitive. Isn't the whole point of a RAG the semantic similarity search? Yes, but your personal notes have a property that makes pure semantic search fail in a specific way. You use the same vocabulary consistently, which means many notes embed to similar positions in vector space, even when they're about different things. A hybrid search approach combining BM25 keyword matching with semantic similarity scores dramatically outperforms, either alone on personal knowledge retrieval. BM25 catches exact technical terms, project names, and named entities, the stuff you actually search for by name. Semantic search catches conceptual connections you wouldn't have thought to keyword search. The retrieval pipeline works like this: run both searches in parallel, merge results using reciprocal rank fusion, then pass the top 10 candidates through a cross-encoder ranker. Models like Marco Mini-LLM run in milliseconds and cut your noise dramatically. Finally, context window management. Don't stuff all 10 results into the prompt. Score them, take the top 3 to 5 based on relevance threshold, and keep your context tight. This architecture is what separates a toy RAG demo from a system that's still useful in 6 months. And now we need to talk about what makes this entire retrieval system actionable: the protocol that gives the LLM the ability to write back. We've built a system that lets an LLM read your knowledge base intelligently. Karpathy's LLM-Wiki concept has a second half that most implementations miss entirely. The LLM should also be able to write to your wiki, capture insights from conversations, link new concepts to existing notes, flag knowledge gaps. That requires a standardized interface between the LLM and your tools, and that's exactly what Anthropic's Model Context Protocol provides. MCP, released in late 2024, is best understood as USB-C for AI agents, a universal connector standard so that any MCP-compatible LLM host can talk to any MCP-compatible tool without custom integration code. Before MCP, every agent framework, LangChain, AutoGPT, custom scripts, invented its own tool calling convention. MCP collapses that fragmentation into one open standard. The critical insight is what this means for your wiki. Instead of a passive RAG system the LLM queries, you now have an active agent interface where the LLM can invoke vault operations as first-class tools. The question is how to actually wire this up, and the implementation is simpler than you might fear. Let's make this concrete. An MCP server is a small process, typically a Node.js or Python script, that you run locally alongside your Obsidian vault. It declares a set of tools in a JSON schema that any MCP-compatible host can discover and invoke. For an Obsidian vault, the essential tool set is 4 operations. Read note takes a file path and returns markdown content. Search vault runs your hybrid RAG pipeline and returns ranked results. Create note takes a title and content and writes a new file. And up note appends or replaces content in an existing file. The Obsidian MCP plugin, available in the community plugin directory, provides this server out of the box with minimal configuration. Point it at your vault path, set a port, restart Claude Desktop with the MCP server, config in your Claude config.json, and Claude now has live access to your entire knowledge base as structured tools. The agent can search before answering, create a note capturing the conversation insight, and link it back to related existing notes, all in one interaction. This is the architectural shift from AI that can answer questions about my notes to AI that participates in building my knowledge base. And the full picture of how all these pieces connect is what we need to see now. Now let's see the complete picture, because understanding the full data flow is what separates developers who maintain this system from developers who abandon it after 2 weeks. A user types a question in Claude Desktop. Claude, operating as an MCP client, sees the available Vault tools and decides to invoke Search Vault with the query. The MCP server resist tool call runs the hybrid BM25 plus semantic search through your vector store, applies the re-ranker, and returns the top chunks with source metadata. Claude constructs a grounded response using those chunks, then optionally invokes create note to save the insight back into the vault. The user gets an answer that cites specific notes in their own knowledge base. The vault grows richer after each interaction. This is the complete loop, and it's running entirely locally if you chose Nomic Embed, SQLite WSS, and a local LLM through Olama. What you've built is not a chatbot with memory. It's a knowledge infrastructure that compounds in value. Now, before you get excited and start building this weekend, there's a critical question we need to confront in the next chapter. Does this actually work better than simpler alternatives? Where does it break, and what did Google learn building GBrain at scale that you should know before you commit to this architecture? Here is a question nobody in this space seems willing to answer directly. If Karpathy's LLM-Wiki approach is so compelling, why did Gary Tan, the CEO of iCombinator, someone with arguably more operational pressure than any of us, build GBrain with an entirely different philosophy? These are not the same system dressed in different clothes. GBrain optimizes ruthlessly for speed of capture. The assumption is that a founder's most scarce resource is attention, and any friction in the note-taking moment destroys the habit entirely. So GBrain accepts lower retrieval depth in exchange for near-zero capture latency. LLM-Wiki takes the opposite bet. Karpathy's design assumes that the value is not in storing everything, it is in building a reasoning layer on top of curated, high-quality notes. The insight density per note is deliberately higher. You are not journaling. You are writing compressed reasoning artifacts. These are fundamentally different cognitive contracts with your future self. The question is not which one is better. The question is which contract you can actually honor. And that answer depends entirely on your workflow, your discipline. Critically, your vault size over time. Let's look at what the benchmarks actually say about that trade-off. Now let's get into actual numbers, because this is where the conversation usually stops being theoretical and starts being uncomfortable. Community benchmarks, pulled from Reddit threads, Discord servers, and a few published blog posts from practitioners running these systems at scale, show a consistent pattern. At under 500 notes, both approaches perform similarly. Retrieval accuracy hovers around 85 to 90% for well-formed queries, and hallucination rates stay low because the context is manageable. Watch what happens as vault size scales past 2,000 notes. GBrain's retrieval accuracy starts degrading faster, dropping to around 70%, because its flat capture model means all the low signal notes are competing for the same embedding space. LM-Wiki holds up better, staying near 80%, but its latency climbs. At 5,000 plus notes, both systems show meaningful degradation unless you have implemented aggressive chunking strategies and periodic re-embedding. The dirty secret is that latency in real-world conditions, on a local machine, not a benchmarking rig, is consistently 2 to 4 times higher than any demo you have seen. And that latency gap is exactly where user habit breaks down. Most people abandon the system not because it stops working, but because it stops feeling instant. That is the cliff we need to watch out for. The benchmark table you just saw tells you when the system degrades. Now I want to tell you why, starting with the failure mode that is simultaneously the most common and the least discussed. I call it context poisoning. Here is how it works. You wrote a note 18 months ago about your understanding of transformer attention mechanisms. That understanding was incomplete. You even left a comment in the note saying revisit this. You never revisited it. Now that note sits in your vault, gets embedded, and when you ask a sophisticated question about attention, the RAG pipeline retrieves it alongside your more recent, accurate notes. The LLM cannot tell which source is authoritative. It averages across them. The output sounds confident, but is subtly wrong in exactly the way your old thinking was wrong. This is not a retrieval bug. This is a knowledge quality bug masquerading as a system. And it gets worse as your vault ages, because stale embeddings do not announce themselves. The embedding vector from a note you wrote 2 years ago looks exactly the same in cosine similarity space as one you wrote yesterday. There is no timestamp signal in the embedding itself, unless you explicitly encode it. The system is silently corrupted, and you will not notice until you act on the bad output. The fix is not technical, it is epistemic. You need a note hygiene protocol, but most developers skip it because it feels like maintenance, not building. That is the trap. Context poisoning is a quality problem. The second failure mode is a quantity problem, and it is counterintuitive. As your vault grows and your retrieval pipeline matures, you might think, more retrieved context is better. More evidence for the LLM means better answers. This intuition is wrong, and it breaks systems in production constantly. I call this over-retrieval. When your RAG pipeline retrieves too many chunks, say 15 or 20, to fill a large context window, something subtle and damaging happens. The LLM stops reasoning from the most relevant information and starts summarizing across all of it. It loses the ability to prioritize. The nuance in your most relevant note gets diluted by the average of all the other retrieved content. This is especially dangerous for technical queries where precision matters. You ask a question about a specific architectural decision you documented, and instead of surfacing that decision with its full reasoning, the LLM gives you a blended summary of 5 related notes that sounds comprehensive, but misses the specific answer entirely. The chunking strategy compounds this. If your chunks are too large, you retrieve fewer but less targeted passages. If they are too small, you retrieve many fragments that lose their original reasoning context. There is a sweet spot, roughly 300 to 500 tokens per chunk with meaningful overlap. But even then, top K retrieval count matters enormously. Most default configurations set K too high. Tuning it down to 3 to 5 for precision queries is one of the highest leverage adjustments you can make. But here is the real question. Do you even know what your current K value is set to? The third failure mode is the one that kills more of these systems than the first two combined. Not because it is technically complex, but because it is psychologically easy to defer. The maintenance loop failure. Here is the reality. A personal knowledge system with LLM retrieval is not a set-and-forget tool. It is a living system that requires a minimum viable upkeep routine to stay accurate. Every time you add a significant number of new notes without reindexing, your embeddings drift out of sync with your actual knowledge state. Every time you restructure your Obsidian vault, renaming folders, splitting notes, changing your tagging taxonomy, without triggering a re-embedding pass, your retrieval silently degrades. And every week you do not write is a week where your knowledge graph ages without compounding. The developers who succeed with this system are not necessarily the best engineers. They are the ones who treat it like a code base that needs commits, not a database that runs itself. The minimum viable maintenance chain is not complicated. A weekly 15-minute audit of notes added that week, a monthly re-embedding pass for any vault section that changed significantly, and a quarterly deprecation review to archive stale content. That is it. But if you cannot commit to that contract consistently, the system will decay, quietably, and in ways that will make you trust it less over time until you stop using it entirely. The checklist on this slide is not aspirational. It is the floor. Now, knowing these 3 failure modes, how does the system actually perform over a real 90-day window? Let's look at the data. Enough theory. Let me show you what 90 days of real usage actually looks like, because the pattern is almost universal among practitioners who have documented it honestly. In the first 2 weeks, query frequency is high and optimism is high. You are testing the system, exploring what it can do, asking it questions about notes that feel genuinely novel. This is the honeymoon phase. It feels like the future. Then, around week 4, something shifts. You start hitting the failure modes we just discussed. A retrieval comes back wrong. A note you thought was current turns out to be stale. You lose 30 minutes debugging why the system returned a contradictory answer. Query frequency drops. Some developers quit here and call the system overhyped. And to be fair, if you built it wrong, they are right. But if you push through week 4 and implement the maintenance discipline, something interesting happens around week 6 to 8. The queries you send change in character. You stop testing the system and start actually using it for hard problems, architectural decisions, synthesizing research across multiple sources, building on reasoning you documented months ago. The hit rate on useful versus useless queries flips from roughly 40% useful in week to 70+% useful by week 10. Not because the system got smarter. Because you learned how to write notes that the system can actually reason from. The system is a mirror of your writing quality. That is the insight most tutorials bury. So what is the honest ROI picture? I want to give you a framing that most tutorials refuse to give because it is not optimistic enough to drive clicks. Month 1 is a net negative. You will spend more time building, debugging, and maintaining the system than you recover in knowledge retrieval value. That is not a flaw, it is the cost of any infrastructure investment. Month 2 is roughly break even if you maintain the system correctly. You are getting genuine value from the retrieval, but the setup and upkeep costs are still visible. Month 3 is where the inflection point appears. If you have been writing consistently and maintaining the vault, you will have your first experience of the system surfacing a connection you had genuinely forgotten. A decision you made 6 months ago, a research thread you abandoned that turns out to be exactly relevant to a current problem. That moment is the proof of concept for knowledge compounding. It cannot be benchmarked in a lab. It only emerges from real longitudinal use. Month 6. Developers who stuck with the system consistently report that it has changed how they write notes, not just how they retrieve them. The act of writing for LLM retrieval forces you to be more precise, structured, and more honest about what you actually understand versus what you vaguely remember reading. The cognitive side effect is arguably worth more than the retrieval itself. But none of this happens if you quit at week 4. And in the next chapter, we will make the decision explicit. Given everything you now know about this system's real costs and real benefits, should you build it, or should you wait? Let's cut straight to the most important question in this entire lecture. Is LLM-Wiki actually for you? We've seen the architecture, we've seen the failure modes. Now it's time to be brutally honest about fit. The system delivers high value for a very specific profile. First, researchers and engineers who are constantly doing architecture decisions. People who generate 10 or more written documents per week and need to cross-reference past reasoning. Second, developers working in long horizon projects where context from 6 months ago matters today. Third, technical writers and knowledge workers whose output quality directly depends on retrieving their own prior thinking. The key signal is this. If you find yourself rereading your own notes to remember why you made a decision, this system was built for you. If your vault has over 500 notes and keeps growing, the ROI compounds over time. But here's the trap most developers fall into. They assume that because Karpathy uses this, it must be universally applicable. It is not. The next scene will show you exactly where this system breaks down. Now let's talk about the cases where LLM-Wiki is the wrong choice, and I want to be specific, because this is where most adoption mistakes happen. Scenario 1, the small vault problem. If you have under 200 notes, semantic search is overkill. A simple Obsidian keyword search with good folder structure outperform a RAG pipeline every single time, with zero maintenance cost. Scenario 2, team knowledge bases. LLM-Wiki is fundamentally a single-user system. The moment you need multi-user access, version-controlled edits, and shared ownership, you are fighting the architecture. Notion AI or Confluence with AI plugins are purpose-built for this. Use them. Scenario 3, the zero-maintenance user. This system requires ongoing embedding reruns, prompt tuning, and occasional index rebuilds. If you want a tool you set up once and forget, this will become abandoned infrastructure within 3 months. The honest benchmark here is Notion AI. It handles 80% of the cross-note retrieval use case with zero setup, cloud sync, and team collaboration built in. LLM-Wiki wins only on depth of personalization and data privacy. Know which battle you are actually fighting before you spend a weekend setting this up. Every technology adoption decision requires a clear-eyed look at risk. Let's map out the 4 critical risk vectors for the LLM-Wiki full stack. First, API cost exposure. Running GPT-4o against a 1,000-note vault with daily queries can run $30 to $80 per month, depending on your query volume and context window usage. This is manageable, but it is not free, and it scales with your vault size. Mitigation. Set hard token limits per query and cache frequent retrievals. Second, data privacy. Every query with context chunks gets sent to OpenAI's API. If your notes client data, proprietary IP, or personal medical information, this is a hard blocker. Mitigation. Go fully local. We'll cover that in the next scene. Third, query latency. The full pipeline, embedding vector LLM call, adds 2 to 5 seconds of latency compared to instant keyword search. For interactive workflows, this is acceptable. For real-time autocomplete, it is not. Fourth, vendor dependency. If OpenAI chasing or deprecates an embedding model, your entire index may need to be rebuilt. Mitigation. Store raw text alongside vectors. Use open embedding models where possible. The matrix shows no deal breakers for the right user profile, but every risk has a real cost. Ignoring them is how projects get abandoned. Now here is the escape hatch for every privacy concern on that matrix. The fully local alternative stack. If sending your notes to any external API is a non-starter, and for many professionals it absolutely should be, you can run the entire LLM-Wiki pipeline on your own machine using Ollama with Llama 3. The trade-off is real, and you need to understand it clearly. Response quality drops measurably. Llama 3 AB at local inference speeds is roughly equivalent to GP 3.5 Turbo in reasoning depth, not GPT-4o. For simple retrieval and summarization tasks, this is completely acceptable. For nuanced synthesis across 20 documents, you will feel the gap. The setup path is straightforward. Install Ollama, pull the Llama 3's model, Replace your OpenAI API calls with local Oyama endpoints, and use a local embedding model like Nomic EmbText instead of text embedding 3 small. Your API cost drops to 0. Your data never leaves your machine. Your query latency actually improves if you have a modern GPU, but degrades significantly on CPU-only hardware. The honest assessment: for a privacy-first solo developer, this local stack is the correct default. Start here, and only move to cloud APIs if you hit a quality ceiling that actually blocks your work. The next decision is not which stack to pick. It is when to start building. Here is the single most common failure pattern I see with ambitious knowledge system projects. Developers try to build the full stack on day one. They spend a weekend wiring up embeddings, MCP server, Obsidian integration, and a custom query interface. And by Monday, they have a half-working system that requires constant babysitting. 2 weeks later, it's abandoned. The correct approach is phased adoption, and I am going to give you the exact sequence. Week 1. Use plain Obsidian with no AI layer at all. Focus entirely on note structure, consistent front matter, clear linking patterns, and a folder taxonomy that will scale. This is not optional groundwork, this is the foundation that makes everything else work. Week 2. Add embeddings only. Run a batch embedding script over your existing vault, set up a local chroma or face index, and test semantic search with 5 to 10 real queries from your actual work. Validate that the retrieval quality is worth the overhead before adding any generation layer. Week 4. Only after validated retrieval quality, add the MCP server and LLM query interface. By this point, you know your vault structure works, your embeddings are accurate, and you have real evidence that the system is solving a problem you actually have. The developers who succeed with LLM-Wiki are not the ones who build the most ambitious version first. They are the ones who earn the right to add complexity by validating each layer. In our final chapter, we will consolidate this into a decision framework you can apply to any emerging AI tooling, not just LLM-Wiki, and show you what signals to watch for as this space evolves. All right, this is the moment the entire lecture has been building toward. Forget the hype. Forget what Karpathy does on his machine with years of curated notes. The only question that matters is, should you build this right now, or are you about to waste a weekend on infrastructure that doesn't fit your actual workflow? I've seen dozens of developers fall into this exact trap. They clone the repo, spend Saturday configuring embeddings, and by Sunday they realize their Obsidian vault has 47 nodes, all written in the last 3 weeks. The system collapses under its own ambiguity. So here are 3 diagnostic questions. Answer them honestly before you write a single line of code. Question 1. Does your vault have more than 500 notes accumulated over at least 6 months? Because below that threshold, a simple keyword search outperforms RAG in both speed and accuracy. Every benchmark confirms this. Question 2. Do you write new notes at least 3 times per week? If your knowledge base isn't growing, an LLM layer adds 0 compound value. And question 3. Are you comfortable owning a Python environment and API key budget, and occasional reindexing jobs? If any answer is no, the simpler path wins. But if all 3 are yes, then you're in the rare group this system was actually designed for. And here's what determines which configuration you need. The decision matrix is more specific than you think. Now let's collapse the entire video into one decision matrix, because nuance without a clear output is just noise. We have 4 variables that actually determine your optimal configuration: vault size, writing frequency, privacy requirements, and your maintenance tolerance. Map yourself to one of these 4 cells and you get a concrete stack recommendation, not a vague depends. Small vault, low frequency. Stop here, use native search. Large vault, low frequency. Consider a read-only semantic index with no auto-update pipeline. Run it manually once a month. Small vault, high frequency but privacy sensitive. Run a local model like Olama with Nomic EmbText. Skip the OpenAI API entirely. Large vault, high frequency, privacy flexible. This is the full Karpathy stack. OpenAI embeddings, chroma or GBrain, LangChain retrieval chain, automated nightly reindex. That last configuration is what this lecture was really about. The other 3 cells exist to tell you when to build it. Most tutorials never show you the exit ramps. This one does. And once you've placed yourself on this matrix, the implementation path is no longer ambiguous, it's a checklist. But the more interesting question is where this entire category of tooling is heading in the next 18 months. Because the query answer interface you just built may already be obsolete by design. Here's the uncomfortable truth about the system you just learned to build. It's already a generation behind the frontier. Not because it's wrong, it's genuinely useful today, but because the retrieval augmented query interface is a transitional architecture. It still requires you to ask the question. The next wave removes that dependency entirely. Let me walk you through the trajectory. Right now, in 2024, we're in the query answer phase. You ask, the system retrieves, you get an answer. That's what this lecture covered. But the pattern that's emerging in research and early production systems is the proactive knowledge agent, a background process that monitors what you're currently writing, detects conceptual gaps against your existing vault, and surfaces relevant notes before you even form the query. Think of it as the difference between a library and a research assistant who reads over your shoulder. The technical milestones required to get there are three. First, reliable streaming context from your active editor. This is partially solved by LSP-style integrations. Second, a persistent agent loop with working memory that doesn't reset between sessions. This is where LangGraph and the new OpenAI Assistance API with thread persistence are pointing. Third, confidence-calibrated proactive interruption. The agent needs to know when OT to surface suggestion, which is still an open research problem. The 2025 to 26 window is when these three pieces converge for individual developers at acceptable cost. But the one thing you can do right now to be ready is in the final checklist. Let's close with the exact actions that separate developers who actually ship this from those who bookmark the video and move on. First, clone the Karpathy nanogpiro not to run it, but to read how he structures long-form technical notes alongside code. That mental model is the real lesson. Second, the one repository you actually want for this system is the Obsidian low GPT combined with a self-hosted Oyama instance that gives you the privacy-safe starter stack in under 2 hours. Third, edit only one file first, the chunking configuration. Chunk size and overlap are the single highest leverage variables in retrieval quality, and most people never tune them. Start at 512 tokens with 64 token overlap and measure before touching anything else. For follow-up topics that build directly on this, study LangGraph for the agent loop architecture, look into the Llama Index query pipelines pattern for more structured retrieval, and watch the Model Context Protocol specification. MCP is becoming the standard interface between agents and personal knowledge systems, and understanding it now puts you 6 months ahead. The trap most developers fall into is building the infrastructure before validating the workflow. You now have the framework to avoid that. The question isn't whether this technology will be part of how developers manage knowledge. It will be. The question is whether you build it at the right moment, with the right scope, for your actual use case. You now have everything you need to answer that correctly.